All right, so hello everybody, I am Shikun Aaron Zhang. I am a research scientist at the Privacy Innovation Lab at TikTok. So today I'll be talking about some crypto and differential privacy stuff that I've been working on to mitigate user tracking in private set intersection. All right, so let's first start by explaining what is private set intersection. You're probably familiar with set intersection. So basically, there's a party X, there's a party Y who wants to compute the common elements that they have. In this case, if there's no concerns for privacy at all, both parties can directly share their sets and obtain the common elements in the set. But if they want to do it with some kind of privacy guarantee, for example, from the party X perspective, he or she doesn't want the other party to know the elements that's not in the intersection set, or the other party doesn't want the same thing either. They rely on something called private set intersection. So in this case, they would only know the common elements, in this case, elements C and D in the intersection without knowing the rest of the elements. And here are a lot of real-world applications of private set intersection. For example, when you are signing up, there's something called private contact discovery. For example, if you are a user of a new messaging app and you want to figure out which of your contacts are actually also users of this messaging app, and the problems you don't want to share all of your contacts with the messaging company, and also for the messaging app company, they don't want to also work with data that's not their direct users either. So you can see there's a need, there's kind of a mutual benefit to use private set intersection in this case for a contact discovery. And there's also other examples such as password checkup features. I think that's provided by Chrome, that it computes the intersection of your passwords with any leaked password found in password data breaches. So it's very clear that you want to use PSI in this case because you don't want to share a password, originally secure password that's not in the leaked password with the service provider. And private set intersection is often the first step used in a lot of multi-party computation. So in this case, you don't want to just know what the intersection is. You also want to do computation on the intersection data. And this is an example about two parties that want to compute on the private intersection. So there's an insurance company X that has a patient's medical history data, including hospital stays or any healthcare use, among other user details. And there is a research institution that is conducting a study on with cancer survivors and how their life choices could affect the cancer coming back rates. So if they want to share their data to work on, for example, an algorithm that explores the correlations between life choices and also cancer coming back rates, they cannot just simply exchange data because, of course, first of all, its health data is very sensitive. And so that's where the computation private intersection could come in to help. So it could let both parties work together, analyze data, and potentially find cool insights without giving away the patient's information. But notice that the most important thing is that neither party would want to reveal their data set, and not only the intersection part nor the non-intersection part. All right, so the commonly used private set intersection protocols are called Delphi-Hillman-based PSIs. There are a lot of math involved in this, and to be honest, I don't really know much about the math here. But the takeaway is that this is a widely used PSI protocols, and it has advantage of easy to use to implement, and also lower communication overhead in practice, and has been applied in many practical systems. But as you can see in the example, this protocol actually revealed the intersection size of the results. And this, as we will talk about later, may actually leak membership information about the party sets in a semi-honest setting. So even though this revealing of the intersection size does not directly violate the intended security guarantee of private set intersection, which is to keep each party's input set confidential. All right, so here is a toy example of how membership inference can be potentially leaked through a private set intersection. So we're sticking with our previous example of two parties, and we are taking the perspective of party Y. So we are not seeing any of party X data. And so for party I, who is honestly participating in the PSI protocol, may still be curious about, what of my items belong to party X or not. And when the first time the party Y pass in their data, it shows that intersection size is 2. And the party Y can actually make a second query to using the PSI protocol, but this time it excludes one row from their data set. And this would actually, when they get their results back, the intersection size now is reduced by 1. So now party Y knows that this row with user C is also actually which is also a common set in party X. So this basically is a toy example illustrating the core concept behind this membership inference attack in the context of the Delphi human-based PSI protocols. All right, so this privacy leakage could result in a curious party knowing the portion of their users who is or is not in the other party's set. So to kind of contextualize this point, consider the health data sharing scenario that I mentioned earlier. So this means that the health insurance company could know a portion of their users in their system are actually cancer survivors that participating in the research institute study. So such knowledge not only violates the patient's privacies, but this knowledge could be potentially utilized to make unfavorable decisions, such as denying coverage or potentially increasing premium for these patients. And there's actually a paper on membership inference attack on the Delphi human-based PSI protocols that's published in USENIX 2022. And we have also improved on this method to further exploit to make the attack more efficient. And the results is on the right figure. So as you can see, with about 27 PSI queries, we are able to infer 3% of the membership of the user base. So basically running 27 queries, you are able to know if 3% of your users are actually in the other data set or not. So it's important to note that the only assumption in this case is the ability to conduct multiple PSI queries. This is often a necessary and unavoidable requirement in practical PSI services. So as you can see, this attack is really practical. And before talking about the protocol that we came up with, let's discuss some real-world challenges. So in existing literature in academia, PSI typically assumes the use of just one identifier per record for the joining operations. But however, in practice, data owners may have varying types and quantities of identifiers that they use to perform matching users on. And that usually is for enhancing the accuracy of successful matches. For example, you can easily envision two data owners using date of birth and name and zip code and phone number to perform such kind of matching results. So this is not just one ID that's being used, but multiple IDs being used. And in the case of using multiple IDs in PSI protocols that we already talked about, it reviews the intersection size. And this could result in a more significant information leakage compared to the single ID-based one. So this is an example of two parties trying to perform some private set multi-ID PSIs, and they're using 3 IDs to be matched. And with a Delphi human-based protocols, either parties can act as an attacker or semi-honest attacker and analyze the patterns in the matched intersection results across all possible subsets of the IDs. So in this case, you can see the number of intersection sizes reviewed is actually exponential to the number of IDs that's being used to perform the match. And even if privacy-enhancing mechanisms such as differential privacy were to be employed to mitigate this leakage, the privacy loss from DP can accumulate exponentially as the number of IDs increases. And this shows a significant challenge when dealing with multi-ID PSI protocols. So there really should emphasize, a need for a well-thought-out PSI designed to effectively address the increased risk of information leakage. All right. So in response to these issues, we have developed this DPCA-PSI protocol. It's a mouthful, but it stands for differentially privacy protected cardinality PSI. So this is to enhance privacy in scenarios where two parties need to compute intersection-related statistics from their private datasets. So there are a lot of components in this protocol. So first, we revamped the Delphi human-based protocol for multi-ID scenarios specifically. And this redesign makes the PSI matching for each key independent, which significantly reducing the size of the reviewed intersection from exponential to linear. And now with the linear, we applied a two-party distributed differential privacy mechanism. In this mechanism, both parties would append the randomly selected dummy records to their input datasets, achieving a differentially privacy guaranteed intersection size. So this results in each party, this guarantees that the intersection sizes that each party obtains are intentionally randomized with a proven DP guaranteed protection. And thirdly, our DP mechanism also introduced only minimal communication and computation overhead. So this ensures that subsequent intersection-based computations are less affected by the noise that's being added. So our approach to the tight DP composition maximizes the number of intersections operations possible within a given DP privacy budget. All right, so we conduct some experiments. You may recall this graph from the previous one. So it was revealing up to 3%, but under our current protocol, it doesn't reveal anything for 30 operations. And the right table shows the efficiency of the protocol. So we calculated the number of dummy variables needed to achieve the DP guarantees. And for example, with an epsilon value of 2 and the input data sizes on the order of 10 to the 7th, our method introduced just a minimal overhead of 0.0%. So to the data set. So this overhead ensures the DP protection of the intersection size while maintaining efficient and practical performance. In addition, this protocol also is very efficient in real-world scenarios. As shown in the table, it's benchmarked against other open source Delphi human-based private set intersection protocols. And it's exceptional in terms of both the computational time and cost. All right, so here are some takeaways from deploying PATs in real-world use case settings. So the security protocols such as, that's security or crypto protocols could still exhibit privacy vulnerabilities in practice. And so consider this case of the review of intersection sites, which is part of the protocol, but could still be exploited for membership inference attacks. And practical requirements can amplify the privacy vulnerabilities. So in this case, the multi-key matching leads to an exponential increase in privacy leakage. So the lessons learned here, I guess, is these crypto or security protocols, they're not inherently designed in the context of privacy and corresponding regulations. For example, it is important for practitioners to recognize the limitations of applying such protocols in privacy-sensitive scenarios or applications. And thirdly, one single PAT, PET, privacy-enhancing technology, might not be sufficient, and synergistic PATs combining the best of both worlds can really be helpful. So in this case, we're combining MPC and differential privacy to ensure both the input and output privacy. And this is a table from the UK's ICO's office. They released a guide on privacy-enhancing technologies. And you can see multi-party computation provides input privacy, and differential privacy guarantees output privacy. So when you combine both, you get the best of both worlds. All right, so we actually, so this is only one possible example, combining MPC and DP as one example of synergistic PATs. And we actually open sourced this DPCA-PSI protocol in PrivacyGo. So the PrivacyGo project aims to harness the unique capabilities of various PATs to guarantee privacy both for the input and output. All right, so I guess in conclusion, the DPCA-PSI protocol demonstrates the intricate integration of various PATs and the engineering innovations, showcasing that with dedicated effort, it is possible to develop protocols that are not only suited for real-world applications, but also effectively address privacy requirements. That's conclude my talk today.